The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, this is the next to the last lecture you'll be happy to know. And today we're going to talk about current regulatory safety issues. I thought it would be really important for you to catch up on what the NRC thinks is important these days as it relates to their safety and regulatory function. So we're going to try to cover a few things relatively quickly, and I went to the NRC website and I said, what are your key current issues? And the list is reactor vessel integrity, which as you probably realize is now reactor vessel embrittlement. Pressurized water reactor sump pump performance, we'll look at that. Many of these issues have been around for 20 years, but they're still there. The reactor coolant system weld issues, they used, and they're getting primary water stress, corrosion, cracking. We've already talked about Davis-Bessey head degradation, so we're not going to talk about that, but that's certainly related to certain weld issues. We've never really talked about fire protection. Fire protection is an old rule that we'll briefly review, and they've got some issues now with some insulation that doesn't meet certain standards. And it's a difficult question for them. And obviously the new issue since 9/11 is plant security and terrorism. We've seen some recent evidence of groundwater contamination, namely in the tritium case. And based on our last lecture, I thought it'd be good to update you on what they call the safety conscious work environment as a safety culture question. So we'll go through them sort of one by one. The reactor vessel integrity issue was in part driven by Yankee Atomic, the Yankee Roll plant. Now, what happened at Yankee was that when the Yankee plant was built back in the late 50s, each reactor was supposed to install a surveillance capsule of the material that the reactor vessel is made of and the material that the welds are made of. And it's all very carefully tracked and monitored. But in those days, in the 50s, they weren't so scrupulous about making sure the capsules were the original vessel capsules and the weld material was the original vessel material. But luckily for Yankee at the time, they did put capsules in, and they did put weld capsules as well. But unfortunately, during the first or second year of operation, the capsules were destroyed. In other words, the holders broke, and they were able to retrieve some, and they had limited amount of data upon which to base predictions. And the way they made these predictions was they put them very close to the core, and over a period of time, they would take out specimens and determine what the degree of embrittlement was. At Yankee, we had a number of specimens early in life, and we had one really late in life, and you couldn't really just draw a straight line curve to it. But most reactors, and pretty much all reactors today, have these in-core specimens that they use to determine whether or not the vessel is becoming overly embrittled. And typically, these are specimens in which they're located in a place in the core, a number of places in the core, where they can get irradiations over time. So what we have had at Yankee was that we were trying to go for a license renewal, and one of the justifications for continuing to operate past 40 years of operation was that we need to show the vessel was sound. Well, in our attempt to try to defend it, and obviously it depends on the weld material and the metal, because some of them depends upon your chemistry of the metal, you have more or less susceptibility to embrittlement. And as I recall, it was copper content, some nickel content, and basically it was very, very key to be able to understand what the vessel was in fact made of, because the performance was significantly different. Well, what happened at Yankee was we spent probably over 2 years trying to convince the NRC that our vessel was fine, based on the limited data that we had. Luckily for us, we had a reactor in Belgium that was in fact also made at about the same time of the same type of metal, and we had their radiation and embrittlement data. The net result was the NRC didn't buy our story. And the key parameters basically that you have to look at is this nil ductility transition temperature, which I know you haven't had the material, so you wouldn't understand. But it's a point after which, at certain temperatures, the reactor will lose a lot of its strength. And in fact, if you shock it with cold water, there's a potential. Should there be a flaw or a crack in the vessel can propagate that crack. And that's why the NRC was really anxious about this particular event. And the concern was, and I believe we talked about it once in class, the issue was what we call pressurized thermal shock. And that phenomenon was, if you're under high pressure, say 2,200 pounds, and you hit a hot vessel with cold water being, ambient temperature water, like from the refueling storage pool, which is obviously not this hot. It could be typically on the order of, let's just say, 60 degrees Fahrenheit. If there is a pre-existing flaw, that shock would, in fact, cause that flaw to grow, possibly rupturing the vessel. Some compensatory actions that we had to take were, and this is the ECCS water, that we raise its temperature to 120 degrees so that the shock would be less severe. And we showed probabilistically that the likelihood of the event, given this design of our system, and given the failure rates of these certain components, would be low enough such that the event was like a 10 to the minus 8 probability event. But this was before the days of PRA, acceptance in the regulatory process. But after all was said and done, we were committing to inspections of the vessel to see if there's any calculated flaws. But at that point, we were going to spend roughly, in those days, $28 million to do a vessel inspection and additional testing for a license renewal of 20 years. And there was no assurance from the NRC that we'd actually be able to convince them that this is not a problem. Interestingly enough, subsequently, the regulators did accept our arguments, but at that point it was much too late to save the Yankee point, so we shut it down. But there's a lot of documentation. There's this generic letter 9201. You want some history on the case, and obviously there are lots of other correspondence between Yankee and the regulator. But this is sort of, if you want to get more information on it, that's a good place to start. You could search. It was a difficult time for us. A lot of reactors also had similar situations, and they had to do a lot of vessel inspections, identifying a lot of fracture toughness. And I think if our department does a material science course for undergrads, this is going to be a major issue. But the phenomenon is pressurized thermal shock. In normal conditions, you're not expecting the reactor vessel to fail because it's warm and hot, but if you hit it with cold water, it's a problem. Some reactors, because some of these reactors want to operate for 60 years, and fluence is an integrated phenomenon. So what they've done, and this gets back to our reactor physics, and they've decided to do low leakage cores, where they manage the core fuel management such that the amount of neutrons escaping from the reactor hitting the vessel is reduced. So that's a major impact on core design. And in fact, the reactor vessel is really the only major life-limiting component in the whole nuclear power plant. You can replace turbines, you can replace condensers, you can replace steam generators. The reactor vessel becomes a little tricky. We at Yankee were actually considering replacing the reactor vessel. We've done some preliminary studies, but it became, for a plant of only 185 megawatts, very difficult to justify. But you theoretically can do it. The other thing that you can do with this is called annealing. And we looked very hard at this concept of annealing. And this was done, it has been done, in reactors, I believe, in Russia for sure, and I think in the Belgian reactor. Annealing is basically taking and heating up the reactor vessel welds, or those zones where you have potentially embrittled conditions, heating it up and allowing the material to relax and restore some of its original properties. And this annealing phenomenon could potentially allow you to get 10 more years of operating life and then allow it to re-irradiate. So annealing is another solution to reactor vessel integrity issues if replacement is not an option. But it's sort of like it doesn't fully recover, and you need to do it more frequently as the more irradiation damage occurs. And so these are some solutions that you might want to think about if you're ever faced in this situation. The next issue, do you have any questions on the reactor vessel one, by the way, before I go on? It's a lot of stuff, but I was prepared to give you some discussions on the kinds of work that we did do to justify operation, but if you don't have the material science background, it's pretty hard to discuss. But the two key areas in this discussion is what is the maximum detectable flaw size? And given that maximum detectable flaw size, should you have a PTS event, would the reactor vessel fail? Or have a crack propagation such that the likelihood of failure would be much higher? And the inspections that you do inside these reactor vessels mean you take all the fuel out of the reactor vessel, and then you do some kind of inspection that will identify what you consider to be the maximum flaw size. And that is the key driver. And there's all kinds of analysis that you can do to show with a certain detectable flaw size this thing is going to be a bomb or not. The other issue is this next issue that I want to talk about is sump pump performance. Now, this issue has been around since the late 1970s. All right? Now, why is this a problem? Well, do you remember when we talked about the need for recirculation? All the water pretty much comes down into the lower containment section and is pumped back into either the core spray system or back into the reactor. But when you have this stuff going on, especially in the containment sprays or maybe in the major pipe break, you potentially can lose a lot of insulation, a lot of debris. Will ultimately end up in the bottom of the sump. And it originally started with boiling water reactors back in the late 1970s, where they have, for these pumps, they had debris screens. And the debris screens were intended to keep the debris from damaging the pump, and possibly even going into the main coolant pumps and main coolant system and actually getting into the reactor vessel. So the NRC had a big issue about identifying whether or not these BWRs, debris screens, would in fact block sufficient water from getting to the pumps and then not allowing water to be recirculated. And this is this net positive suction head. And that was, can you get enough water pumping through the pumps to be able to get it to the appropriate places, whether it be the reactor vessel or the sprays. And it's basically causing potentially a failure of the recirc pump or cavitation of these pumps. Both are not good things. So initially, as you look at it, it was associated with insufficient cooling. Then in the early 1990s, well, there's a red guide. Let me just write down the red guide so you can kind of read it here. There's a red guide that was issued. It was on the sump question. It was red guide 1.82. And it was largely in response to BWRs. And they had a generic letter as well, which was 85-22. So you can see how long ago this issue started. And 1979 was the first time they got this thing going on debris blockage. They did some research, they did some preliminary analysis, and they basically had the BWR people fix certain things. But they concluded that it was kind of okay for PWRs back at that time. Then they started looking at that, and now we're talking into the late 1990s. And they said, well, gee, maybe PWRs are also susceptible to this problem. And the issue was very similar, but they had, the screens that they had were somewhat different in design than the BWRs. And they felt that initially the PWR screens were fine. But then they had some experiments and they had some events that occurred that suggested that, well, we have a similar problem here. And they then began looking at it for PWRs. Now this is a current issue. And they've done evaluations, the NRC has done evaluations, and as has the industry. And what they concluded was that some of this debris could pass through the screen and could get into the core. And the issue basically is, if it goes into the core, it could obviously block some fuel assemblies. And the industry responded by doing some analysis saying that, yes, if it blocks some fuel assemblies, there are a sufficient number of holes in the core barrel or areas where water can in fact come into the core that it is not a so-called imminent problem, which meant that they would be allowed to continue to operate until this issue was technically resolved. And the issue resolution was size of the screen mesh and the impact on the core. So we're fighting two things. If you make it too fine a screen, you're not going to get water to the pump. If you make it too loose a screen, you'll get debris into the core. Both are not good. But this is still a very active safety issue. And the last bulletin, I guess, was bulletin on this one, 2003-01. And it still requires licensees to demonstrate that this will not be a problem for them. Now you remember the differences. I've written down a couple of things. I've written down regulatory guides, I've written down bulletins, and I've written down generic letters. Do you recall the differences?
So the bulletins we have to respond to.
Exactly. The bulletins have to be responded to. Generic letters are heads up, may request some information. Reg guides are, this is a way to comply to this question. So you've got all kinds of different approaches that the NRC has taken to allow the industry to be aware of a problem and how best to get the solution of this problem. And if you go on the NRC website, you'll see a lot of industry presentations. If you go under meetings, you'll see sometimes NEI presentation. And you'll get from that website slides of what people have said, but from the industry's perspective. Now this one is in long-term core cooling on core inlet flow blockage, which basically said, well, we've got a lot of this debris coming through, and it's going to impact the core, and this is our analysis showing that we do not believe we have a problem under various scenarios. Could you open a window? I'm warm as can be. Okay, the next issue is reactor coolant system weld issues. Now this graphic again comes from their website. Now, these are all the areas in which there are weld issue problems. Now, you're looking at this like, oh my goodness, this is not, these things are kind of wearing out, aren't they? First you had, we all know about the upper head control rod drive issues relative to Davis-Besse and other plants. We vaguely or briefly mentioned pressurizer leaks. Welds coming into or out of the reactor vessel and around the pressurizer, around the main coolant pumps, the lower reactor vessel head, where in current plants all the instrumentation penetrations come through the bottom head. And these areas are now becoming also very, very important. And they have a common root cause. And the root cause is a certain type of alloy that's used in the welds and the buttering of the welds, which is the materials that are associated with this alloy 600. And it's primarily a primary stress, water stress corrosion cracking, which we talked about. It's very clean water, and the determinants are temperature, what the residual stresses are at those locations, and how much of this nickel-based alloy and how it was applied to these various welds. Now, I've just listed a few plants that have been affected. Now, once you detect this problem, there's a solution. Well, first you got to detect, which is a lot of measuring devices. And you can imagine if you're in these areas, it's probably a relatively high radiation zone. So these are not easy to do. But if you find these flaws, the solution is grind it out and weld overlay. Take different weld metal and weld overlay so that you can avoid the leak that may occur. Now, we also have, in this case, we have a different type of response. Now, this alloy 600 and 182 and 82 are basically the structural materials that keeps these pipes together. And just to get some perspective again on timing, and I think you're going to see a theme emerge from this discussion. On the timing question, this was first detected in 1989 at Calvert Cliffs in Maryland. And the issue here was a pressurizer. It's usually the hottest component, and during the fabrication it probably had a lot of stresses, and it's on the heater sleeves, which with the pressurizer heaters, you know, they get pretty hot and toasty, and that's where the welds began to start leaking. And that resulted in information notice 90-10. Then we saw, I think you remember that chart, timeline chart, we had this thing at the Bougie plant in France. And that occurred roughly in 1991. And you recall the industry response to that event was different type of problem. We don't have this design here. Our vessels' heads are made differently. And the NRC pretty much bought that argument based on NEI and EPRI analysis. And that bought some time, but not a lot of time. It then became interesting once again when people started looking at various inspections. NRC mandated some inspections of all of these types of welds as they in fact occurred. And the sequence was, well, back in 1993, the conclusion was that these cracks were axial. Remember the axial discussion? That they would result in detectable leakage. detectable leakage, and you could be seen visually. So, based on their analysis, and this was their basis that said, oh, it's okay, it's not a problem for U.S. planes. If it's going to leak, it's going to be axial, it's not going to be circumferential, which means the whole thing is apart. And we can see it in terms of the detectable leakage, because we don't, and we can see it easily by simply taking the visual examination. However, when they started doing some of these inspections in 1994, they found at Point Beach that of the control rods, the CRDMs, they had lots of indications. I think that was 49 indications. And that sort of got them going. And they used what they called eddy current testing. So it was not visual. It was more scientific, where they were looking for flaws. And in the process, they also started looking at Oconee, and you remember the Oconee Unit 1, I think it was. Was it Oconee 1? Oconee 1. In 1994, they also found 20 indications. And the sequence goes on and on and on until the NRC finally decided, with a lot of these findings, that this stuff was failing. And they gave a generic letter 9701, which attempted to do a probabilistic analysis of the likelihood and of these cracks occurring and the potential damage in terms of growth. Now, what do you sense that's going on here? Growth. What do you sense that's going on? The NRC is trying to understand this problem. They know it exists. They're not prepared to shut down every plant to do visual inspections, but they're saying to the utilities, you must give us a better case to justify why you should be operating. And in order to do that, we need to understand why these things are failing. What is the history of this fabrication? How was this stuff stress relieved? Was it, when they fabricated this particular nozzle, this particular piece, was it highly stressed when they assembled it? And based on that information, they were able to say, the utility were able to say, we don't think these susceptible to cracks. Or there was a function of time that people were able to say, well, we don't expect to see this for another 5 years, based on the environmental conditions that these welds had to experience. But the evidence was fairly well mounting quite a bit, that said there's a real problem. And as you remember, in France, what they said was, this is way too expensive to do all these visuals, we're going to replace all the heads and stop the problem. That stopped this problem, but it didn't address necessarily any of these others. So after they began to see more and more of these things, out came Bulletin 2001-01. And that basically said, all right, we're done with this looking. We've seen evidence at Oconee 1, Oconee 3, Arkansas Unit number 1. They actually saw boron deposits at some of these plants, remember that? And said, okay, now we're going to have to do something very serious. And in fact, this is the first time that we've seen circumferential cracks. And this gave a lot of people a lot of pause. Because for the first time, they were basically saying that these things could come apart quite more dramatically than what we assumed back in 1993, 1994. Well, after they did some more of these inspections, up they came with bulletin number 2002-01, and that kind of gave us the Davis-Bessey finding. And luckily, as we saw, there have been all kinds of, no damage really was resulted from this, but it gave the industry one of the closest near misses ever. So, you know, I don't know how much more to go into this, but they ultimately required a lot of licensees to identify their highly susceptible plants, and visual and non-visual inspections were mandated to avoid any of this stuff in the future. And right now, people are actually doing this. The one thing I want to talk about is what they now call, I'll keep it on this board, it's BMI, bottom mounted instrumentation. And this was found at the South Texas project. And this has to do with the same darn alloy 600. Now just imagine a bottom mounted instrumentation to leak. All right? It's a cold, I mean it's a hot, dark place. And the core is right here. You're not going in there during operation, or even after it's shut down. Of course, it'll be taken out to visually inspect and repair. So this could be another major issue, but so far they have not yet identified any other plants besides South Texas that has this problem. That's not to say it's not occurring, because there's no reason why it should only occur there and not anywhere else. We already talked briefly about the pressurizer, and some of these plants, I should say, B&W, everybody that manufactures these things do it in a different way. And it really is related to the manufacturing, how these components are made, how the head is designed, that affects the stress levels. So it is vendor unique. And that's why some cases Westinghouse isn't susceptible, combustion engineering and B&W are, in all of these different areas. So you can't just blanket say it's all PWRs have this particular problem. So I think what you're going to be seeing in the near term is, as more of these leaks develop, this is a fix. This can be fixed by weld overlays and relatively easy to inspect, as can these be. They can replace pressurizers. This becomes a little trickier because there's a lot of in-core instrumentation, and it's like a forest down there. Heads can be replaced, but the challenge and the additional cost and expense of doing these inspections is very, very great. Any questions on that one? No? Fire protection. Fire protection has its own very interesting story. This over to fire protection. Obviously, the objective is to prevent fires. Now let's really go back to history. How many of you remember the Browns Ferry fire? How many of you have heard of the Browns Ferry fire? One. Okay, we can start from there. Anybody remember what plant they just restarted after about 10, 15 years of being shut down? Browns Ferry. Unit 1. Now, I don't know when this plant came actually started operation. But they just spent, I think, was it actually $2 billion
That sounds right.
to bring the plant back into operating conditions. But on March, why is it always March 1975, we had the Browns Ferry fire. The plant was then in operation, and they were trying to fix leaks in the containment, and between the containment and the outside. And they were using a candle to see if any air was coming in. Well, the candle worked. They were able to detect air, but the candle caught the insulation on fire, which lasted for how many hours? 7 hours. During that time, as you might imagine, and they had this in the cable spreading room, now, the cable spreading room, we haven't really talked specifically about it, but that's the place where all the power and instrumentation cables come to the plant, control cables. And they ended up burning 1,600 cables. About 628 of them were important to safety. You can imagine what was going on in their minds. They essentially disabled many of the safety systems, and they had to jury rig, and as I remember, using the cooling from the control rod drive systems to cool the core. That's how we got fire protection in the U.S. industry. And as a result of that, we have this, some people call infamous, other people call famous Appendix R. Since Browns Ferry, there hasn't been another fire in the U.S. industry affecting safe operation. There have been fires in turbines and stuff like that. Nothing like this. So what do they require? They required, again, these are for plants that have already been built and operating. To the extent you could, some people separated train A from train B. Now you kind of know what train A and train B means. And if you can't separate it, because all of these things come into the cable spreading room, ultimately, the wires, you have to have insulation, specific insulation designed to allow for a certain time before the fire can affect the wiring. 2-hour wraps, 6-hour wraps, fire doors, fire watches, and obviously a lot of detection and suppression. Now, with electrical fires, you're probably not crazy about throwing water on. So they had halon systems. Halon. And now they use some other type of material that's more environmentally friendly. But this, when this thing goes off, you don't want to be in that room because you can't breathe it. You got it. Some rooms don't have any equipment, and they hand fight it in some places. But you do and end up doing, as the Appendix R approach changed, they started using fire PRAs, identifying what the likelihood of a fire is and what the consequences of that fire may be. The consequences are important. So you're looking at a fire hazards analysis. Which includes the likelihood and consequences of the fire on safety. And obviously you have fire loading issues, especially during outages. I'm sure you're all familiar with these major fires that occur at churches. People are doing repairs on the church, they burn the whole church down. Well, during outages this becomes very sensitive because at this point you're in fact working potentially with welding equipment and stuff like that. Very, very serious concern, and people have done a lot to try to control fire loadings in these areas. But to this day, it's not a settled case. So they've replaced some of this deterministic analysis with a probabilistic analysis using the tool of fire hazards analysis, identifying risk significant systems, and then apply your mitigation or prevention system accordingly. In the process, the NRC has done some tests with some of this insulation. It was supposed to be fire rated. And I don't know if you were here, we had one of the fellows from the NRC come by, and a member asked about this Hymek insulation, which is used routinely at many of these plants. And when the NRC tested it, they found that it didn't do its 2-hour job. It melted, the covering of the insulation melted, allowing exposure to the actual cables, which then would have burned. The NRC has now dealing with this, because this is, again, in many of the plants, and I think the most recent determination is relative to this Hymek stuff, is that they issued another generic letter. So you can see how recent this is. Generic letter 2006-03 for the licensees to evaluate this and take compensatory action should they find a lot of this in key areas based on the fire hazards analysis. And compensatory action could be putting somebody in the room where this insulation is and sitting there and watching. If there's a fire, then you push the fire alarm. That's perhaps a little more draconian, but that's a quick action. But they conclude that in areas where there's both fire detection and automatic suppression, even when you have this stuff, the NRC remains, I'm quoting, assured that those plants' overall fire protection scheme will ensure the safe shutdown of the reactor. So if you have this stuff, you could end up replacing it, and you're probably, if you don't have detection and suppression in that same way, you're going to have to do it. So that's fire protection. And the fire PRAs is something still people are trying to work through. They have other types of fire protection equipment. There's lots of thermal lag is another brand, but that's sort of been resolved as best I can tell. Any questions on this one? Okay, this is Ashley's favorite. Ashley did a study some years ago about an airplane crashing into a nuclear power plant. And as a result of 9/11, they have turned nuclear power plants into, what does this remind you of? Prison. They have turned nuclear power plants into prisons. And this is probably, normally you'd see razor wire here and a couple of fences, and yes, I think you see some razor wire here. So there's at least an outer fence and inner fence separated by motion detectors and electrified wire potentially. And you have these pillboxes around the site. Now these pillboxes are positioned so that if anybody decides to come on the site with a gun and try to take over that facility, this person or persons can kill that person anywhere on the property before they get indoors. So if you go to San Onofre, the plant that I'm most familiar with in the States, where I observed this, they have, I don't know how many of these around, but it's very clear. It's lit up at night, and you're not getting in this place. And if you think you're going to be carrying a gun in there, you're going to die. There's no issue. At Yankee, our security staff, I was not comfortable with these guys having guns in the control room. You never know when a worker's got an issue, even though you do all kinds of site profiling and whatever. A gun in the control room wasn't a good idea, but the NRC said you must have guns. Handguns. And you know, it's really, you look at some of these rifles, they're well armed. So they had to upgrade the physical security, It's not a welcoming place to go or work. You had to show that your particular plant is capable of being, withstand a aircraft impact. And had we had more time, we can show you some of the issues that we looked at with Ashley some years ago about, it's not just about the containment, it's about other things that could be damaged. And then they have the things called design basis threats, which are, imagine a certain type of intruder or intruders. You have to be able to repel these people, at least for a time, until you get the Army, Navy, Marines, Air Corps, whatever, local police to come and help you out. It's true. And this design basis threat is continuing to evolve based on what the sophistication of the terrorist could be. And they have, not a live ammo, of course, but they do have people assaulting the plants, and we do certain tests and drills every 3 to 5 years. The theme of this is not that we're going to be able to, it's not the utility's job to fend off the intruder or knock it out. It's the military's job and the police job to assist. Their job is only to hold off, to avoid them from getting into the critical areas of the plant. And some people say, why don't we put missile batteries at some of these nuclear power plants that used to shoot down airplanes? And the answer is that's not our job. The job is that of the federal government to protect any installation, including nuclear power plants. So at this point, this has been a hugely expensive operation. The security staffs are larger than the operating staffs at these plants. And I'm talking, they also do 24/7, 365. So this is a huge new expense, and these guys have to be trained and well trained. And you've seen some recent stories about guards sleeping on the job. Obviously, that's not acceptable. Any questions on this one? Groundwater contamination. This is a surprising thing, but it occurs. And typically, I don't know if you remember, but this is about 5 or 6 years ago, Brookhaven National Lab had I think it was in their refueling water storage tank or some tank containing tritiated water leaked. And Brookhaven is all in that. In a nice area, mid-island, in other words, islands 120 miles long, maybe out, 40, 50 miles. In a nice residential area, it's a nice research lab. They had a leak from one of their earlier operating reactors, and it was triggered. Very low level, that did not exceed the drinking water standard, but they had such a brouhaha, they almost shut the lab down because of the public outcry, demanding it be shut down. And it changed the lab. It used to be a nuclear energy laboratory in part, now it's pretty much a basic science lab. But they had a lot of reactors there. They had a high temperature, fast flux reactor. They also had some graphite reactors, so they were one of the early pioneers. Because of this very low level of tritium getting into the groundwater and migrating, almost shut the laboratory down. In the nuclear world, we've had leaks at Indian Point, Braidwood, Callaway, Dresden, Byron, Colorado, and Quad Cities. Again, a lot of it coming from the spent fuel, where tritiated water does occur. And in some cases, it came, like in Braidwood, from I think they had leakage in some of their vacuum valves on the secondary side, on the primary side of their plant. And the leakage was known, not reported on time, and when reported, created a huge stir in the local population. What they had to do at Brookhaven was drill monitoring wells and suck up the water. Now, tritium, you can't really do much with it. What they did with that water, I don't know. But they were pumping the water. And maybe storing it, don't know. They're apparently going to be doing the same at these leaks. Now, this Braidwood plant actually got a notice of violation. And this was issued in 2006. And the violation basically cited them for, under Part 20, which is this radiological effluent part, was they did not make the necessary surveys to identify the leak. They were not assuring that the public got less than 0.1. This number is REM per year. Had no way to assure, even though they didn't get it. And there were failure. Their failure was largely to identify the leak and deal with it. They just kind of ignored it. They did release 3 million gallons of water. A lot of water over time. And this went back from November 1996 to March 2006. So it's not that they didn't know it was happening. It's just that they failed to properly report it and failed to deal with it. And they had numerous leaks over that time period, the largest of which was 3 million gallons to the groundwater pathway. The industry, of course, responded. We're going to commit to do this, and the other things, sometimes not do. But most nuclear plants have monitoring runs, but not where apparently this particular leak occurred. And remember the reactor oversight process? They got a white finding. And that white finding triggered this investigation, and they then also triggered this apparent violation. I don't know what the fine was, but my guess is they probably got one. Okay. So here's what they had to do. The public got really outraged. The usual demands that the plant be shut down. The report, they didn't think that this leak was within the reportable domain. And unfortunately, it was. They have what they call radiological effluent tech specs, RETS. And under those tech specs, they should have routinely reported even small leakages, which they chose apparently not to do. But even though the levels were low, they had a problem. Let me take a minute to do the enforcement process, which I think is interesting. For minor violations, these are the things that were found in the inspection report, still green, no issues. You self-identify, they identify, not a problem. Then you get it says the non-escalated process. Severity level 4, they go from 1 to, I think 1 to 5. And these are violations and related to green significance determination process, SDP. Green findings. You're okay, but you got a violation. Did you fail to restore compliance? Yes. Boom, you get it. Okay. We're not even talking to you anymore. If you did, if you failed to restore, no. Did you fail to put it in the corrective action program? Is it a repetitive finding? Is it willful? If all these are no, in other words, you put it in your corrective action program, you dealt with it responsibly, you're not going to get a violation. It'll be a violation, but not what they call non-cited. You won't get dinged for it. If for other licensees, namely, I would say that if this was something that you, I don't know why this would be, other licenses, we're not going to talk about power reactors. But if you're in escalated process, this is severity level 1 and 2, and 3 violations related to white, yellow, red, and significance determination findings with actual consequence. So you got a problem, you got an impact, and you couldn't have a white with a consequence. Was it, what does it say? First non-willful level 3 in this period of time? Yes. Credit for corrective action? Yes. no, I guess. It's notice of violation, but no civil penalty. Civil penalty is the fine. From a public perspective, getting a notice of violation is not a good thing. From a public perspective, getting a notice of violation and a civil penalty shows you're really, really not doing your job. So if it was first non-willful no, and you get credit for identification, then you can kind of play this as well. If you didn't identify it and you didn't correct it, you're going to get hit twice with the base fine. And violations related to white, just basically you just get a notice of violation. So you don't want to be on this path, for sure. But this process has been very effective at getting the utilities focused on trying to improve the situation. But violations and fines do occur. I picked up 2 recent enforcement actions. This is at Byron, just to give you a sense of what kinds of things they're citing you for. Now this was a white finding, Part 50, Appendix B, which was really quality assurance, that was your quality program. And you didn't, and this was in design control, fail to take timely corrective action after identification of extensive corrosion essential to service water riser pipes, and failed to verify the adequacy of the methodology and design inputs in calculations that supported the decision to accept 3 degraded essential service water pump risers for service. What does that say to you? What message was NRC telling Exelon about what they did from an engineering perspective? They couldn't get you on a specific regulatory noncompliance item, right? But they got you on your corrective action quality control program, which is sort of this catch-all Appendix B. And Appendix B says, you didn't analyze this right and you made a crappy decision about why you should continue to operate with degraded service water pipes. That's a whole different thing where you fail to follow the text specs or fail to comply with regulation. You failed to follow good procedures. And you made a lousy decision on how you decided that this was still okay to run. Very significant in my opinion. The next one. This is at Comanche Peak. This is at Comanche Peak. Now, this was an interesting one. They had diesel generators supposed to supply backup power. They had a white finding, tech spec violation, and it says, while the plant is in modes 1 and 2, 2 diesel generators capable of supplying off-site power to 1E equipment, which is the safety-related buses, have to be operable. Now, from this period, November 1 to November 21st, while the plant was in operable condition, you're supposed to get blah, blah, blah power, it was inoperable. And action was not taken to restore operable status within 72 hours or be shut down. Specifically, the complaint was, the emergency diesel generator was made inoperable as a result of painting activities. Okay? Due to the paint having been deposited and remaining on at least 1 fuel rack in a location that prevented motion required to support the operation of the emergency diesel generator. This caused the diesel generator to fail to start. All right? So who's got the ball on this one? The poor painter? Who's watching the store? The point of this slide is that even a tiny thing like painting can get you in trouble if you're not careful about what you're painting. Okay? So those of you who start working in this industry, you got to keep these things in mind. And the reason I pick these is because they're very different, but they can mess you up. Right? If this diesel generator fails to start, it's a problem. And the only reason they detected it was it failed to start. Then they started looking, why did it fail to start? Oh, this thing got stuck because somebody painted it. Okay? Then they look back and say, when was the painting job? That's how they pick the time of infraction. So it's not rocket science, but very important. Okay, I just want to summarize. You know, we all talk about this great nuclear performing record. 92% capacity factor, everything is great, the industry is booming, everybody's making money. But as you saw from a little litany of key safety issues, they've been around for a very long time. And when you start thinking about the pressure vessel integrity and the pipe welding and the primary system integrity itself, these are going to be coming and continue to come unless people decide to fix fundamental problems, and hopefully in the past they will. But these issues remain. The safe operation still requires this vigilance that we need, attention to detail, and in my opinion, strong NRC oversight. Because in my view, had not the NRC been as strong as it was, and in some cases people argue it's not strong enough, you'll fall into this complacency trap. As our friends at Exelon did at Braidwood when they tolerated these 3 million gallons of water without even thinking about the consequences. The role of the industry and NEI at EPRI are important because the NRC will tend to go to one extreme about what the solution ought to be, and the industry said, well, let's be a little more reasonable. And with the onset of probabilistic risk assessment, risk-informed performance-based safety determinations, we have a shot at sort of maintaining that. Is this safety significant or not kind of discussion? So this is the one that makes me a little nervous. We're all bragging about the high capacity factors, and yet when you think about the things that we just went through, we're not done, really, in assuring the safety of these plants. So any reactions or comments? No? Okay. Now, next week's our last class. Scheduled is, I'll do a quick review of the material that we covered during this term, and also provide some insights as to the advanced reactors that we're talking about. Please hand in the homework assignments so I can get them done and grade submitted. I think there are two missing sets right now. There's no homework for this class, and there won't be any homework for the following class. But I want you to spend the time to do the ones that have already been assigned. Okay, questions, comments, suggestions? Good? All right, thank you.